Hello, welcome to our presentation for our NRC CoSpace Robots Challenge 2024. We are Team unITE, competing in the rescue category. First, let me start off by introducing ourselves. On the left, we have Jin-Chen, who is our coder and builder. In the middle is Kwantong, also our main coder and builder. Finally, on the right is myself, Jin Yang. I'm the group leader and assistant coder. We are all experienced in Python and C++, and this is the first time we have ever participated in this competition. The summary of the challenge. In CoSpace Rescue Challenge, we are required to develop and program strategies for virtual robots. These robots navigate through virtual worlds to collect objects. The key to success is using a camera mounted on the virtual robot to detect deposit areas, swarm lamps, traps, obstacles, and objects. The team with the most points at the end will be declared a winner. The rules of the game. All teams must code a program to the virtual robot for this challenge. The game will take place in Virtual World 2 and is single-player mode. All teams will use the blue robot and the game will run on their own machines. Each game lasts around 6 minutes and teams will complete in 2 rounds. The team with the best overall score across both rounds will be the winner. Moving on to the penalties. Running out of the map results in a 10-second penalty, and running into a trap will cause the loss of any collected objects. Here shows the overview of the virtual robot. The virtual robot consists of 3 ultrasonic sensors, 2 RGB sensors, 1 compass sensor, 2 motors, 1 LED, and lastly 1 camera. Now, I'll be giving a brief explanation of the control panel. Load is used to load the program into the robot. Relocate moves the robot back to its original position, and quit exits the game. The map provides a minimap for the game, while the camera shows a map overview. The view option gives the camera's perspective. You can also capture images or video during the game. The AI interface is where programming happens, and the debug program displays system data. The compass sensor measures direction in degrees, and the ultrasonic sensor measures distance in centimeters. The color sensors detect the red, green, and blue values to identify different surfaces. Moving on to the scoring system. The scoring system limits the robots to collect a maximum of 6 objects at a time, unless they are unloaded or deposited into the collection box. Objects disappear once collected. The gray areas of the map represent swarm lands, where robots' speed is reduced by 80% once you cross over into the swampland. A robot is considered to be in a swampland if any of its color sensors detected it. Next, traps and object collection box. Traps are outlined in yellow and contain label tags. These tags help the robot identify traps and collection boxes. If a robot falls into a trap, all collected objects that hasn't been deposited in the collection box will disappear, and points for those objects are deducted. The object collection box also has an label tag, which the robot uses it to identify ownership by detecting it with its own camera. Moving on to our strategy. Our strategy focuses on guiding the robot to the blue deposit by utilizing a combination of tag detection, wall sensing, and boundary navigation. To ensure optimal movement, the robot detects and follows the outer wall of the area, adjusting its course as needed. By following direction through walls, it helps steady and maintain a steady course and avoid obstacles. The result that we got was the robot successfully detected a tag and aligned itself towards the blue deposit. By following the outer wall, the robot maintained a steady course and avoided obstacles efficiently. The boundary navigation strategy allowed the robot to fine-tune its movement, ensuring precise positioning at the deposit. Our conclusion: the wall sensing benefit. It maintained a steady course, helped us avoid obstacles, and the tag detection and boundary navigation ensured accurate alignment towards the deposit, which help achieve precise positioning. Here is an example of our gameplay. An example of applying these concepts beyond a competition is in waste sorting using color sensors. Robots equipped with color sensors can differentiate between various types of waste based on color. For instance, plastics, metals, and paper often have distinct colors or markings. By developing software in Visual Studio 2022, we can process input from these sensors, enabling the robot to categorize and sort waste efficiently. This leads to more efficient recycling and less waste in landfills, contributing to environmental sustainability. Our journey, we have been using ChatGPT to assist us with coding in Python, C++, and C. It provides clear explanations and helps us understand complex concepts by adding comments to our code, making it more detailed. Additionally, Gemini AI has been invaluable in enhancing our productivity, whether it's handling complex data analysis or preparing study plans. For example, it analyzes our study patterns and suggests the most efficient way to prepare for our exams. The end of our presentation, and thank you for listening so far. Thank you.